70% of the human body is water, providing a massive reservoir of hydrogen nuclei. For MRI, every one behaves as a microscopic quantum magnet. The hydrogen nucleus is a single proton with an intrinsic property called spin angular momentum. Because the proton is a charged particle with a spin of 1/2, it generates its own magnetic moment. Under normal conditions, these individual magnetic moments are randomly oriented. The thermal energy of the body causes the protons to shift and tumble constantly. This random distribution ensures the microscopic magnetic fields cancel each other out. On a macroscopic level, the tissue remains magnetically neutral. This baseline state of quantum chaos produces no measurable signal. Generating data requires an external force to break the symmetry and organize the spins. That force is a static magnetic field, conventionally labeled B0, which defines the z-axis of the system. When protons enter this field, they undergo Zeeman splitting. The B0 field forces the spins into two distinct energy levels, one parallel to the field and one antiparallel, separated by a specific energy gap. This is a statistical distribution. Because the parallel state is lower in energy, a minutely larger population of protons settles into that orientation. This diagram shows how MRI shifts from quantum to classical physics. By isolating the slight statistical preference of the population, we extract a single macroscopic vector. This is the net magnetization vector, M0. At equilibrium, it rests parallel to the main magnetic field. Distilling billions of quantum variables into this single entity creates a classical target that MRI hardware can predictably manipulate. The M0 vector experiences a constant rotational torque from the B0 field. This torque causes the magnetization to rotate around the z-axis in a motion called Larmor precession. The speed of this rotation is locked to the magnetic field strength. At 1.5 Tesla, the Larmor equation dictates that hydrogen precesses at approximately 64 MHz. Identifying this exact resonance frequency allows the scanner to calibrate the energy pulses required for the next stage of the process. A vector resting at equilibrium parallel to the z-axis cannot be detected by MRI hardware. It must be moved out of alignment. Technologists apply a secondary magnetic field, a radiofrequency pulse labeled B1, tuned to the 64 MHz Larmor frequency. This resonant pulse transfers energy into the system, pushing the net magnetization vector away from the z-axis. In a 90-degree tip, the pulse rotates the entire vector into the transverse, or XY, plane. Moving the vector into the transverse plane transitions the system from a passive equilibrium into a highly coherent signal-generating state. The moment the radiofrequency pulse ends, the system begins returning to equilibrium through two concurrent physical pathways. The first is transverse relaxation, or T2, which governs the fate of the vector spinning in the XY plane. This shows the mechanism of phase loss. Local variations in the magnetic field cause neighboring spins to precess at slightly different rates, causing them to fan out. The resulting signal decays. Within one T2 time constant, only 37% of the transverse signal remains. T2 decay is an entropic process. The macroscopic signal vanishes because the spins lose phase coherence, not because they are losing energy. Simultaneously, the system undergoes longitudinal relaxation, or T1, along the vertical z-axis. Unlike T2, the T1 process requires a thermodynamic energy transfer from the spin system back to the surrounding molecular lattice. This green panel highlights the vertical regrowth of the magnetization vector as the protons return to their lowest energy state. Recovery is slow. The vector regains roughly 63% of its original magnitude after one T1 time constant. Because this relies on physical interaction with the surrounding molecules, T1 determines how quickly the system resets for the next measurement. Precession, phase loss, and energy recovery occur at the same time, requiring a unified mathematical model to track the results. The Bloch equation is the governing dynamic model for MRI. The first term calculates the classical rotational motion. The middle term accounts for the entropic phase loss of T2. The final term maps the thermodynamic energy recovery of T1. The Bloch equation tracks the trajectory of the magnetization vector as these concurrent processes unfold, providing a mathematical map of the spin system. The loss of the transverse signal is a separate physical event from the return of longitudinal energy. Phase coherence often vanishes long before the longitudinal vector regrows, meaning the detectable signal disappears before the system has reached equilibrium. The true trajectory of the magnetization vector is an upward spiraling cone. This rotating, spiraling magnetic field induces the voltage in the scanner hardware. The raw data is the mathematical decomposition of this 3D spiral into recovery and decay curves. The geometry of this spiral dictates the electrical signal captured by the scanner. These physical constants explain how a scanner differentiates between various parts of the human anatomy. The molecular structure of fat, muscle, or pathological tissue changes the local magnetic environment, which alters the specific T1 and T2 times of that region. Different tissues produce different spirals. Tissue A may have a tight, rapidly decaying path, while tissue B decays more slowly. Technologists time the energy pulses and readouts to catch the exact moment these spirals diverge, creating the contrast needed for an image. MRI scanners map the solutions of the Bloch equations for millions of localized voxels, converting variations in atomic relaxation rates into diagnostic imagery.